Today we're carrying on with question 2, working on part B. We completed part A in the last lesson. So here we have a diagram of a cone with a couple of measurements on and a reminder that things are not to scale. So the diagram shows a solid cone with a radius 5 centimeters and a perpendicular height 12 centimeters, both of which are indicated on the diagram. The total surface area is painted at a cost of 0.015 per centimeter squared. Calculate the cost of painting the cone. Now remember how they told us it was a solid cone. So that means it's all of the ice cream cone piece of it, plus it is this bottom piece as well, because we need to have that as well as the surface area is the complete solid. They do tell us that the curved surface area A of a cone with radius r and slant height L is A equals pi r L. Fantastic, that will help us a lot because we need that curved surface area plus the circle. But when we look at this, we think again, hold on. We have the perpendicular height, 12. This 12 belongs here. We don't have the slant height, L. So the first thing we're actually going to have to do is calculate what is the slant height. But remember we said this is perpendicular height, which means that is a right angle. And there we have a beautiful right angle triangle. We see right angle triangle and we're looking for a length. The first thing we try is Pythagoras. So we know that L squared, I use cursive L so they don't get confused with ones, equals 12 squared plus 5 squared. So L squared equals 144 plus 25 is 169. And then we can square root both sides to get that. L equals 13. So now we have that slant height is 13. So now we're ready to do a surface area. So we've said the surface area equals the curved surface area, so pi times the radius times the slant height plus that circle on the bottom, which is pi r squared, so 5 squared. So surface area equals, and if we plug all of this into a calculator, pi times 5 times 13 plus pi times, well, 5 squared is 25. We get 90 pi centimeters squared. Okay, remember we don't put units in our calculations. Units just come in at the end. I've left the pi in here for now because I'm going to be calculating more. So I want to have a nice accurate amount that I'm calculating with, because they didn't ask us for the surface area. They asked us for the cost. So we have $0.015 per centimeter squared, and now we have the number of centimeters squared. So we would then know that the cost equals all of those centimeters squared times the cost per centimeter squared, which gives us a total of 4.24. So $4.24 is the total cost for painting that cone. It is paper 4, so we continue. The cone is made of metal, and it is melted down and made into smaller solid cones with radius 1.25 and perpendicular height 3 centimeters. So now we've got 1.25 and we've got 3, and that's now our cone. Calculate the number of smaller cones that can be made. Well, if we're looking at one cone, melting it down, making little cones, we're talking about volume. What is the volume of that big cone? What is the volume of a small cone? And then how many little cones can we make out of that total volume? So we're going to need the volume of a cone, and they don't actually tell us in this case. There's no hint as to where you're going with this question. So you need to be familiar. So our volume is 1/3 pi r squared h. The volume of a large cone equals 1/3 pi. Large cone is 5 squared, and the height was that perpendicular height of 12. Plugging all of this in, we get a beautiful answer of 100. The volume, 100 pi, I beg your pardon. Yes, you mustn't forget that pi. Remember, we're working with that exact and precise answer. Volume of the small one, 1/3 times pi. R is now 1.25 for the small one, perpendicular height 3. And that gives us 1.5625 pi. Okay, also, yeah, okay, we've got decimal, but we keep that pi separated. So now we need to say, okay, we've got the volume of the large, we've got the volume of the smalls. So how many smalls can we fit into the large? We're looking at division. So our number of small equals 100 pi divided by 1.5625 pi, and that gives us 64. So there are 64 smaller cones that you can make out of the one big cone. That takes us to the end of question 2. Question 3, we start a new question, so we start a new topic. The diagram shows a field A, B, C, D, and we are seeing triangles, and we are thinking all sorts of different things because we can see triangles. So we can see A, B, C, D is a funny shape, but it's 2 triangles. We have triangle ABC, which is a right angle, so Pythagoras trigonometry. And we have triangle ACD, which doesn't have a right angle. So we'd have to be thinking of the sine rule or the cos rule. So they ask us then to calculate the area of the field ABCD. So let's break it into 2 triangles. Okay, triangle ABC and triangle ACD, then we can add them together. So triangle ABC equals, there's our traditional 1/2 times base times height. And that gives us 50 times 70 is 3,500 meters squared. Everything is in meters. Triangle ACD, well, now we can't use half base times height because we don't have any perpendicular relationships here. So how is the other way that we can do the area of a triangle? We have that area equals 1/2, let's not use that big A, so the area equals 1/2 AB sine C. So C has to be the angle between the sides A and B, and look at this, we have side, angle, side. So we are set up to use sine for area of a triangle. So it would be 1/2 times one side times the other side times sine of 40 degrees. So 1/2 times 150 times 110 times sine of 40, I am not doing in my head. When you plug this into a calculator, you get 3535.33. So we have the area of each triangle. Now we can add them to get the area of the whole field. So area equals 3500 plus 3535.33. Area equals 7035.33. Then we must stop. 7035.33, 7035. No information in the question, which means our answer is to 3 significant figures. So our answer here is 7040 meters squared. because we're rounding this to 3 significant figures. They then ask us path area, perimeter. So the perimeter of the field ABCD. So let's just take a moment to think of that perimeter. The perimeter is AB plus BC plus CD plus AD. We don't want to get confused by this 100 in the middle. So AB we know is 70 and CD is 110. So BC and AD are the fun ones we get to calculate in order to be able to do this. So remember ABC, we had that right angle triangle. BC sits opposite that right angle, which makes it the hypotenuse. So let's do BC first. We know that BC squared equals, A squared equals A squared plus B squared. So the two sides on that triangle were 70 and 100. So BC squared equals 70 squared plus 100 squared. So BC squared equals 14900. Then we can square root both sides to get that BC equals 122.065. Now, how are we going to do AD? Because AD was in this triangle, which doesn't have a right angle. But remember when we said that, we said, oh, okay, we have to think of sine rule and cos rule. So sine rule, we would need A over sine A, B over sine B. Only got one angle here, so that's not going to work, which leaves us with the cos rule. So cos rule, C squared equals A squared plus B squared minus 2AB cos of C. So who lines up with A, B's, and C's in this question? Well, this here is A, this here is D, which would be a B, which make this one big C, little c, and there is sine C. So it does work. We can use our cos rule for this triangle to get this length of AD. Don't even need to rearrange. So we know that AD squared equals, our sides are 100 and 110, our angle is 40. So it would be 100 squared plus 110 squared minus 2 times 100 times 110 cos of 40. So we're going to put all of that into our calculator at once. So AD squared equals 5247.022. Same as before, when you got a square, you're going to square root. AD equals, square root of that gives us 72.436. They didn't ask us for BC and ask us for AD, they asked us for the perimeter. So now we go back to that very first statement that we made. Perimeter equals 70 plus 122.065 plus 110 plus 72.436. So our perimeter total all the way around the field comes to 374. 374.5. Again, 3 significant figures. So it would be 375 meters for 3 significant figures. So in paper 4, keep out an eye for rounding, keep an eye out for mixing up techniques. It's all going to happen here. Because now we're carrying on. Part C, calculate the shortest distance from A to CD. So from A to CD. So this distance here is going to be shortest when this is a right angle. Okay? So if you look at it nicely, we've got some triangle things going on here. So let's redraw that triangle so that we can see what we're doing and our examiner can also see what we're doing. So we have A, we have C. We didn't go all the way to D, so let's just call that point X. This was 100, AC was 100, and this angle here is 40. So we're now dealing with a situation where we have a right angle triangle. That shortest distance from A to CD we now got is AX. So we have an angle, we have a side that we want, we have another side, right angle. We are looking here at SOHCAHTOA. So dealing with our 40, we have the opposite and the hypotenuse. Opposite and hypotenuse takes us to sine. So we now know that sine 40 equals opposite, well, that's our AX that we want to calculate, over hypotenuse, that's the 100 that we have. So we want AX alone, so we're going to multiply both sides by 100. We have AX equals 100 times sine of 40. We can plug that into a calculator and we get 64.27 equals AX. Angles go to one decimal place. So we have 64.3 equals AX. That shortest distance from A to CD is 64.3 meters. And they carry on with our beloved triangles. In the next question, B is due north of A. Find the bearing of C from B. So, B is due north from A. Find the bearing of C from B. So, we want that one. So let's now redraw again so we've got everything close to where we're working. And we have this length here is 17. So how are we now going to get the angle that we want, which goes all the way around here? Well, we can see we've got the straight line. So that straight line is going to be 180. So what we need to find is a piece of that angle that falls in the triangle. And again, we have a right angle triangle and we have two sides. Dealing with an angle, so we are looking at SOHCAHTOA again. So the angle is sitting here. So the 100 is the opposite, the 70 is the adjacent. We don't have the hypotenuse in this case. Opposite and adjacent takes us to tan. So let's call this angle X. Because we want 180. I'm doing this a different way around to when I practice this. Okay, so let's go with it. We have got opposite and adjacent, yes. So we have tan of X equals 100 over 70. So X equals tan to the minus 1, well, it will be 10 over 7. So if we then take our calculators, 10 to the minus 1 of 10 over 7, we get 55. 0.0079. Okay, so we're not going to need those ones because they're far on the side, but we're going to keep them now while we're calculating. So we now know that x is 55.0079. We know that the full bearing is the 180 plus that. So bearing equals 180 plus 55.0079. The bearing equals 235 degrees, 0.0 to 1 decimal place. So a bearing, though, remember, we give as 3 figures. So it would be 235. Question has come through about whether we'd redraw this diagram in pen or pencil. I would probably redraw it in pencil because when I'm drawing, I want to have that ability to erase things. But do make sure that you're using a nice soft pencil so that the examiner can see what you've drawn. You don't want to be using like an H or a 2H because it's far too light, and when the paper scans, then the examiner can't see the diagram. And especially in this case where I've invented my little X and then I've used him, I want to be sure that my examiner can see where did my little X come from? What do I mean by little X? So any questions relating now to this triangle work that we've covered? Because the next page is question 4, changing topic again. Are we happy with the triangles? See the value of SOHCAHTOA, Pythagoras, sine rules, and cos rules. Okay, it looks like everybody's happy, so let us move on to question 4 for the last few minutes. And as soon as you see it, you know you're working with transformations. So, we have a grid, we have a funny shape, and they're calling it a flag because they say draw the image of flag F after translation by the vector 6 minus 2. So before we get started on that, the question has come through, are you expected to learn all of the formulas in the book? And yes, you are. There's no formula sheet at IG Math. You need to be comfortable with all of them. So, translation by a vector. Remember, vectors always move x and y. So we're going to move 6 in the x, so plus 6. So I'm going to start from this end of my flag. 1, 2, 3, 4, 5, 6 in the x. But I'm also moving down because I've got minus 2 in the y. So 1, 2. This is now the base of my flag. And my flag stick goes 1, 2, 3 on the line, and then the triangle is formed like that. And to make things nice and easier for my marker, I'm actually going to label that with part 1. So there is my translation by the vector, 6 in the x minus 2 in the y. Next one. Flag F, after rotation through 180 degrees about minus 20. So rotation through 180 means it's going to be flipped all the way over. So that flag, the pointer of the flag, is going to point up instead of down. So let's find our center of rotation. Minus 20. There is our center. So the way I like to do this is I'm going to connect to my center of rotation. Then 180 is going to split me out to the other side because my angle here is 180. So then I'm thinking my flag is flipping all the way over. So I'm going to go 1, 2, 3 for the stick, and then 2 for the triangle. You guys would be doing this with a ruler, hey, so that your flags are a lot more beautiful than mine. And I'd label this one part 2. And the last one that they ask us for, flag F after a reflection in the line y equals x. So again, we need that y equals x. Now remember, he runs through 0, 0, 1, 1, 2, 2, 3, 3 because y is always equal to x. So we need that reflection line running down. And then our stick is going to start in the same point. So 1 blocky and a half, half a blocky and a 1. We've confirmed that we're going to go 3 down and then form our stick and our flag. And that is part 3. Again, with a ruler, beautifully neat. Question has come through of when you work with the transformations of like this, do you need to write down the coordinates of where your image is drawn? No, you don't. You just need to draw the image. Often in the mark schemes, you will find the coordinates there, and that is so that the person who is marking the paper can actually see precisely and make sure, and then there's no discrepancies or whoops, mistakes by any markers. They know exactly where each of those images must be. So you are just drawing your image with a ruler, labeling it neatly so that they can see exactly which piece is which when it comes to your diagram and your transformation that you have done. Part B gives us another grid with a triangle this time. They ask us to describe fully the single transformation, single one only, that maps triangle P onto triangle Q. So P onto Q. Now the thing is that the only way that we can get a difference in size is an enlargement. So we have an enlargement. But to describe fully, we need, for an enlargement, we need a center of enlargement and a scale factor. So to find that center of enlargement, we join the vertices. So this one is this one, and we carry on. This one is this one, and we carry on. This one is this one, and we carry on. And even my dodgy crooked lines all meet at 0, 0. So the center is the origin. So center of enlargement is at 0, 0. And our scale factor P onto Q. So we have 1 over 2. So the scale factor, we've shrunk this triangle, scale factor is 0.5, a half. So we've come to the end of time, so we will carry on with the rest of this question next time we do this paper.